So what if the equations are not separable or not indirectly separable? We will talk about the other forms for ordinary differential equations we can solve analytically. Okay. So what if the equations not separable and now indirectly separable means not homogeneous? Okay. Then that is the third type. We will talk about the ordinary differential equation, which is called the exact equation. Okay. Exact equations. So what is the definition of exact equation? What the exact equation look like? We will write the ordinary differential equations like the standard form, which is mxy dx plus nxy dy that is equals to 0. If the left-hand side is a total differential of u, then we say this equation is an exact equation. So if the left-hand side, the left side can be written as a total differential, then that means the u is equals to the u dx plus the u dy that is equals to 0. So if the mxy dx plus nxy dy equals to du dx plus du dy, then we say this ordinary differential equations is an exact equations, which means the du over dx has to be equals to mxy. Du over dy has to be equals to nxy. And that means the du squared dx dy, that will be equals to the mxy over dy. Du squared dx dy equals to the nxy dy, dx. And we know that for these two equations, the left-hand sides are the same. So the right-hand sides will be equal to each other. So dmxy dy will be equals to the nxy dx. And if the dmxy dy equals to the nxy dx is true, then this differential equations is an exact equation. Okay. So this is the preconditions to decide whether the first ordinary differential equations is exact or not, and this is sufficient and necessary precondition equations to check the ordinary differential equations, whether it's exact or not. So thus that is the necessary and sufficient condition for an ODE to be exact. Okay, so this is very important. And what if some equations is not exact, is not satisfy these conditions, but it can be exact with some modification? Then we can also solve it analytically. Okay. And we will go to our fourth form. Okay, so some equations cannot be an exact equations directly. And we need a small modification on the equation, which, what is this small modification we mean? Which is multiply by some function gxy, which is now to be 0, and some function is called the integral factor. Okay. And by using this integral factor, we can make the if the dgm over dy equals dgn divided by dx is true, then we say the gm dx plus gn dy equals 0 is an exact equation. Okay, so by using this integral factor to modify the first order differential equations, we can make such ODE to be exact. And it will be, usually it will be very complicated if gxy is a function of both x and y. But if the gxy is only function of either x or y, then it's solvable and it's easier to solve. So, but if the gxy is only function of x or y, then it is easy to solve. And we can, so if, let's assume the g function, that integral function is only as function of x, right? Then what we can do is the dgm over dy, okay, is equals to g dm dy, okay, because the g is only as function of x, and plus, oh sorry, it's equals to the dgn over dx, so dgn over dx, that will be n dg over dx plus g dn over dx. Okay, and if we will divide the gn from both sides, so dividing gn from both sides, okay, both sides, then we have 1 over n dm over dy equals 1 over g dg over dx plus 1 over n dn over dx. And if we put the g part on the left side, we put the n part on the right side, then what we have is 1 over g dg over dx equals 1 over n dn over dx minus dm over dy. And we will use such equations to find what is our integral factor g. So the purpose of deriving this and get this equation is to trying to derive what is our g, okay, to get gx. And we will make examples of using the exact or indirectly exact equations to solve ordinary differential equations analytically. Thank you.